Welcome to This Explainer. Imagine for a second that you are a film director, but instead of shooting the next massive Hollywood blockbuster, you are directing something even more important. A high-scoring, flawless answer for your Cambridge computer science exam. Whether you are taking syllabus 0417, 0478, 2210, or 9618, the core challenge you face is exactly the same across the board. You are sitting there with limited time, staring at a blank page, and you have an examiner waiting to be impressed by your scene. But right now, we have a major problem in our production. Let's look at the dailies. You know, the raw footage from two of our students tackling a real Cambridge past paper question on hexadecimal representation. Picture this. On the left side, we have Alex. Now, Alex has a brilliant memory, unbelievable recall. Alex completely overloads the page with raw computer science facts. We are talking binary conversions, 16-bit systems, MAC addresses, you name it. But there is absolutely zero analysis. None. It's just a massive data dump on the page. Then, on the right side, we have Sam. Sam's problem is different. Sam completely rushes the scene, Sam misses the specific command word requirements, completely ignores the context of the question, and just writes down a basic generic definition before immediately moving on. Look, both of these approaches are total box office flops, and you can see the red pen marks all over them. They lose marks, but not because these students don't understand hexadecimals. They lose marks because they haven't structured their scene correctly. They don't know how to direct the action. Well, today we are going to fix that. We are going to build your blockbuster answer scene by scene by cutting out all the filler and focusing strictly on the core action.
Okay, let's dive into this and look at our production call sheet for today. We'll start with Section 1, the empty scene. Then we move into Section 2, the 3 explanatory layers. After that is Section 3, the method mark sequence, followed closely by Section 4, avoiding examiner pitfalls. Finally, we'll wrap up this masterclass with Section 5, the final cut. Before we start shooting, I want you to read this quote on the screen very carefully. The topic hexadecimal representation should be taught as part of a connected computer science structure rather than as an isolated definition. Honestly, this right here is the golden rule. A highly successful exam answer doesn't start with you just memorizing a vocabulary list and regurgitating it. It begins with you fundamentally understanding the specific digital problem that hexadecimal representation actually solves. Why does it even exist? What kind of data or device is involved in this specific scenario? And what practical consequence does this have for a user, a system, or an organization? Think back to Alex. When Alex dumped all those raw, unconnected facts onto the page, Alex treated hexadecimals as an isolated definition. And guess what? The examiner doesn't want a dictionary. The examiner wants to see a connected web of ideas. They want to see that you actually understand the plot. Section 1, the empty scene. Setting the context for hexadecimal representation. And hey, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Right, so to build that connected web we were just talking about, we have to start with the empty scene and set the correct context. The very first step is decoding the command words in the prompt and applying the correct structural framework. Let's break down the specific assessment objectives you'll face in computer science. When you look at an exam paper and see command words like describe, explain, or evaluate, you need to realize they are asking for completely different scenes. Describe simply means paint a picture of what it is. But explain means tell me how it works and why it matters. To absolutely nail this, top-tier students use what we call the PEEL framework. That stands for point, evidence, explanation, link. It is literally the ultimate structure for process-based topics. Now, what's really interesting about this slide is the contrast. Take a look at the left side. A description is safe, but it's incredibly shallow. It just tells the examiner what the device, process, or method actually is. For example, hexadecimal is a base 16 number system. Great, that's safe, it's shallow. Best case, that gets you 1 mark. Now look over at the right side. An exam-level explanation tells the examiner how it works and exactly why it matters. This is where that PEEL framework does the heavy lifting. You clearly make your point. You provide evidence or precise technical vocabulary. You explain the underlying mechanism. And crucially, you link it back to the specific context given in the question. And here's a pro tip. Examiners usually expect both description and explanation in these longer answers. If you just jump straight into explaining without clearly naming the concept first, which is exactly what our student Sam did earlier, your response sounds completely confused or incomplete. Let's do a quick mental challenge right now. Imagine a 30-second timer counting down. Look at these 2 distinct approaches on the screen. Can you spot which one successfully uses the PEEL framework to move from a shallow description to a deep, high-scoring explanation? Yep, it's the right side, exactly. Because it names the concept, it explains the underlying mechanism of how it functions, and it gives the explicit why. Moving on to section 2, the 3 explanatory layers, building the scene layer by layer. So you're probably wondering, how do we reliably construct that high-scoring, Peele-structured explanation every single time, without fail? Well, we are going to build your scene layer by layer. Consider this your official computer science success blueprint. The absolute biggest trap students fall into is thinking they know a topic inside out, perfectly, right up until they sit down in that quiet exam hall and actually try to express it under severe time pressure. Suddenly, all those great ideas just float around in total abstraction. We need a systematic, repeatable way to take those red pen marks from our early dailies and transform them into green check marks. Here is how you do it. High-scoring answers always transition smoothly through 3 distinct explanatory layers. First comes layer 1. This is the simple explanation using everyday language. Think of this as you explaining hexadecimal to your grandparent. You'd say something like, well, it's basically a way to write really long binary numbers in a shorter, much easier to read format. Good, but not enough for the exam. Then we step up to layer 2. This is the technical explanation, where we inject the correct subject vocabulary. Now you're introducing terms like base 16, nibbles, MAC addresses, and memory dumps. Better, but we are still not done. We absolutely must reach layer 3. This is the exam explanation perfectly shaped to score marks under time pressure. This is where you actively apply the Peele framework. You structure that technical vocabulary into a logical, flowing sequence that directly answers the specific command word. Let's run a rapid mental rewrite attempt right now in your head. Take Alex's messy raw data dump from earlier. How would you consciously shape that into layer 3? Well, you take all those floating facts about 16-bit systems and organize them. You'd identify the contrast, memory versus storage, or data versus information, because these theoretical foundations control the direction of the whole answer. Computer science reasoning becomes dramatically stronger once you establish those boundaries clearly on the page.
Which brings us nicely to section 3, the method mark sequence, the 4-step technical approach. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
All right, to consistently hit that top-tier 3rd explanatory layer, you need a highly disciplined technical method. Let's dive into our first interactive workshop challenge, the data scan. I want you to imagine a complex computer science chart or data table on the screen, and you have exactly 60 seconds to extract the core trend. To do that, you use this 4-step technical approach. This is your method mark sequence. Step 1, identify the demand of the question. What is the examiner actually asking for? Is it process explanation, hardware selection, or maybe a security judgment? Step 2, classify the correct concept or process. Step 3, explain the sequence or structure, step by careful step. And step 4, connect the explanation back to the context. This exact structure is what produces clear, high-scoring answers instead of a bunch of random facts written out of order. Let's apply it. Imagine you're looking at a complex Cambridge exam question about a factory automated system that is displaying error codes. Your mission is to rapidly extract the core trend using these 4 steps. So what's the demand? You need to explain the error code display. What's the concept? It's hexadecimal representation. What's the sequence? Binary data from the automated system is converted into hex so the human operator can easily read it. And finally, what's the context? The factory floor. Boom. You've just diagnosed the exact type of thinking required, making your answer hyper-focused and highly economical. I want to pause on that step 4 for a second, connecting back to the context. This is where most students completely drop crucial marks. Generic responses rarely, if ever, gain full marks in a Cambridge paper. If the question is set in a school, an office, a retail environment, or a secure network, your answer must stay rigidly inside that specific context. Real-world transfer matters immensely because it converts your rote memory into actual demonstratable usefulness. Let's look at the list on screen. Hexadecimal representation isn't just an isolated textbook chapter. The exact same patterns appear in mobile phones, website HTML color codes, databases, automated factory systems, banking services, and robotics. When you repeatedly connect the technical concepts to these specific familiar technologies, you are proving to the examiner that you truly understand the reason the concept exists in the first place. This is the link in your Peele framework. If you just define hex and don't link it back to the specific real-world context provided in the prompt, like Sam did, you are literally leaving marks on the table. Section 4, avoiding examiner pitfalls, cutting the distractions.
Now it is time for our second mental challenge. We call this Find the Flaw. One huge reason students find hexadecimal questions difficult is that the surface features of a question can severely distract from the real underlying idea being tested. You might see a question about a network router and fixate entirely on the device name. Or you see a MAC address and you just start defining network hardware, completely ignoring the deeper data representation process that the question is actually assessing. Let's look closely at the traps principal examiners warn us about year after year, represented right here on this slide. So what's going to lose you marks? Using vague wording instead of precise technical terms is a massive one. Another huge flaw is confusing similar terms, like mixing up memory and storage, or a compiler and an interpreter. Missing vital steps in a sequence is a remarkably quick way to lose method marks. Failing to answer within the given context, as we just discussed, is a total classic error. And finally, stating an advantage without providing a reason. If you write, hexadecimal is better, the examiner is asking, better why? You need to say it's better because it takes up less space on the screen, substantially reducing the chance of human error when a technician is copying a MAC address. Error-aware preparation is infinitely more useful than just memorizing correct facts. You absolutely need to know where the traps are hidden so you don't step in them.
This brings us perfectly to Challenge 3, Speed Writing. Imagine putting 30 seconds on a visual timer right now. Your task is to mentally construct one single perfect Peel paragraph following this logical answer ordering. In exam writing, clarity of sequence is everything. It's the whole ballgame. Computer science topics are heavily process-based. Your answer improves dramatically when the steps are ordered logically. Step 1, explain the mechanism first. Step 2, state the consequence afterwards. Whatever you do, do not jump forwards and backwards in your process. Do not mix general theory with context examples in a chaotic way that breaks the flow of your explanation. Tell the examiner exactly how it works, and then, as a direct result of that, what the consequence is for the system. If you can paraphrase this mechanism accurately without relying on a rigid, memorized sentence you crammed the night before, that knowledge is far, far more likely to survive the pressure cooker of the exam hall.
Section 5, the final cut, the practical self-check. We have finally arrived at the last act, the final system. You've built your scene, you've carefully layered your explanations, you've applied the method sequence, and you've successfully navigated the pitfalls. Now we do the final cut. Let's look at the cheat sheet recap. We've established 3 unbreakable rules today that absolutely guarantee top marks. Number 1, command word decoding. Number 2, Peel framework application. And number 3, a time management matrix that ensures logical structuring. But before you confidently submit this blockbuster answer to the examiner, you need to run one last practical test. And this brilliantly illustrates our ultimate quality control, the 4-question self-check. Look at your answer on the page and ask yourself these 4 prompts aloud. Number 1, what is it? Have you clearly defined the core concept? Number 2, how does it work? Have you meticulously mapped out the logical mechanism? Number 3, where is it used? Have you anchored your explanation firmly to the specific real-world context of the question? And number 4, why is it better or worse than an alternative in that specific situation? Have you evaluated it? If you can confidently answer those 4 prompts based strictly on what you've written, your topic is ready for the examiner. Your scene is perfect. If not, you need another cycle of reading, explanation, and recall. This layered structure, this constant bridging between theoretical ideas and practical application, is exactly what elevates your response from an average, middle-of-the-pack grade to a top-tier Cambridge mark. It sharpens your reasoning instead of just repeating definitions. So, we've taken the raw, messy footage of your computer science knowledge and edited it into a structured, high-scoring masterpiece. Now, listen closely because this is crucial. Students who implement these exact computer science strategies see an average improvement of 2 whole grade boundaries, but that only happens if they practice consistently with our weekly videos. Here is your final reminder. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. I want you to drop a comment below right now with your target grade for computer science and the absolute biggest challenge you're currently facing. Our team responds to every single comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. But before I let you go, I want to leave you with one final thought. If hexadecimal representation is the universal bridge between complex, unreadable machine code and human understanding, what other digital languages in our world are quietly waiting for you to decode them? The exam is just the first scene, my friends. How you use this logic to build the future in the real world, well, that's the rest of the movie.